Welcome to Are You Chemistry GCSE Ready? This playlist takes you through loads of example questions and guided solutions for every single topic in your chemistry GCSE. So it's a perfect way for you to test your chemistry knowledge. If you feel like you need a quick review or you just want the ideal revision companion for these videos, then make sure to download my free chemistry GCSE revision notes. I've linked them in the description below. Or if you're ready, let's dive straight in.
Okay, noble gases. So what do their electron configurations all have in common? Well, the point is, because they're all in the same group, that is group 8 or group 0, they all have complete outer shells. So they don't need to gain or lose electrons to fill that outer shell and to become more stable. So they're all very stable. How do their properties link to their uses? Well, they're inert or unreactive. So that very much links to this idea that they have complete outer shells. So they're not gaining or losing electrons from anywhere. So they don't tend to react with things. And that's really useful if we have something where we would like to avoid some corrosion or any potential combustion or oxidation. So one of the examples that we had in the notes was to do with welding and having it in an atmosphere of argon to stop that hot metal reacting with the oxygen surrounding it. Okay, the other thing about your noble gases is we can have a look at the density, and we find that their density increases as you move down the group. So at kind of towards the top of the group there, your helium, for example, can be used for its low density. So for things like helium balloons, and it's also useful because coupled with the fact it has a low density sort of float, and it's also unreactive, it means that it's not going to be flammable. So hydrogen also has a low density but would be very flammable, for example. So helium could be a better option for something like that. Okay, why do all alkali metals react in the same way? And it's because of the property that they share, that they all have one outer electron. So what they will do is they will all lose this electron to get a full outer shell when they react, which means that they react in the same ways. What kind of compounds do they form, and how does their reactivity change down the group? So they form ionic compounds when they react with nonmetals, so going all the way back to what we did about ionic bonding there. Your alkali metals will lose that electron and the non-metal will gain that electron that your alkali metal has lost to form these ionic compounds. How does their reactivity change down the group? It gets more reactive the further and further down the group you go, and those reactions get more and more vigorous. Okay, and as a very brief explanation as to why that would happen, as you go further and further down the group, the atoms get larger and larger and larger, so the outer electrons get further and further and further away from the nucleus. And that's important because the nucleus is positively charged, your electrons are obviously negatively charged. So those two things are actually attracted to each other. So the further away the outer electron is from that nucleus, the easier it is to get rid of that outer electron. Okay, you add sodium, which is one of my alkali metals, to water, explain your observations, and then use a balance symbol equation to explain the products of the reaction. So really, you need to have learnt these from your notes. We get fizzing or effervescence as the hydrogen gas is being produced. You have your metal, in this case your sodium, floating on water and moving around the surface of the water, and that's because this metal, sodium, happens to be less dense than water. And then with sodium, you get your metal melting and forming a sphere. Because sodium has, for example, a lower melting point than lithium, it will actually melt during this reaction as well. Now, also from some previous topics, but in this topic as well, you should know that you have the following equation. You have your metal plus your water. If it reacts with your water, gives you this metal hydroxide and hydrogen gas. So in this instance then, let's think about this particular circumstance where we have sodium is my metal, Na. I'm adding it to water, H2O. I get a metal hydroxide, and the metal is sodium, so I get sodium hydroxide. Now, sodium, we know, is our alkali metal, and therefore it is in group 1, and therefore, as we have mentioned, it will lose its outer electron to become a positive ion. So it's got a charge of +1 as an ion, and hydroxide has this charge of -1. So that's fine. Those charges are both balanced in terms of figuring out the formula for my metal hydroxide. And you should know that hydrogen gas, remember, it's diatomic, so it's H2. So I can write my metal, sodium plus water, H2O, is sodium hydroxide plus hydrogen. And then I need to balance things. So at the minute, on my left-hand side, there's 2 hydrogens, and on my right-hand side, there's 1, 2, 3. 1 from the sodium hydroxide, 2 from the hydrogen gas. So I need to add a 2 in front of that sodium hydroxide to get a few more hydrogen on my right-hand side. But now I need to add a 2 in front of the H2O to get more hydrogen on my left-hand side. But now I've got 4 hydrogen on my left-hand side, 2 times the H2, the 2 in the H2. And on my right-hand side, I only had 3. So now I needed to add the 2, that's where that 2 came from, in the metal hydroxide. And now I've got 1, 2, 3, 4 on my right-hand side. So those are now balanced, but what I've done by putting that 2 in front of my sodium hydroxide on my right-hand side is I have added 2 sodiums to my right-hand side, and I only have 1 sodium on my left-hand side. So I need to put a 2 in front of that sodium as well. Now, let's add the state symbols. So we've got solid, my sodium is a solid that I add to my liquid water, and then I get this aqueous sodium hydroxide, and my hydrogen gas is obviously a gas, so putting in the state symbols there as well. Now, with these different reactions, you should learn all of the ones that are in your notes, and this one appeared in your notes off by heart. I'm just showing you if you are stuck in your exam, or if you forgot, or if you're not the kind of person who can learn those kind of equations without understanding where they come from, how you could have come up with that equation with your own knowledge at this point in the course.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, first thing to know for your tips and tricks is your noble gases are actually quite simple, okay? So there's a lot of recall that you need to know. Make sure you know and are happy with all of those mind gaps in that part of this topic. They don't do a lot of interesting things in terms of reactions because they are unreactive or inert. Next, for my alkali metals, if you have a good understanding of ionic bonding, then these alkali metals are much easier, therefore, to understand. And that's how I was able really to write that equation without looking at the notes on that previous slide. More vigorous reactions can be shown off in different ways. So more energy might be given off, you might have more bubbles that are being given off, but you can still just say, in terms of the observation, that you're having a more vigorous reaction here. And remember, they get more vigorous the more reactive these metals are, and that's as you go down your group, because those atoms are getting bigger and the electrons that need to be removed are getting further and further away from that nucleus.